Standards, codes, and datasheets. Design compliance and documentation. This module is about engineering discipline. Control valves fail just as often on paper as they do in service, and most of those failures trace back to misunderstood standards, poorly prepared datasheets, or incomplete testing philosophies. Standards are not bureaucratic overhead. They are compressed field experience. Datasheets are not paperwork. They are design instructions that follow the valve for its entire life. If Module 10 was about surviving the process, Module 11 is about surviving procurement, fabrication, inspection, and commissioning. ISA and IEC standards. Image valve standards exist to ensure that performance claims, sizing methods, and test results are repeatable, comparable, and defensible. IEC 60534 series. The IEC 6534 series is the global reference for control valve performance and testing. It covers valve sizing methods, liquids, gases, steam, flow characteristics and CV definitions, pressure recovery and choked flow, noise prediction, cavitation and flashing limits, testing and performance verification. Engineering significance enables apples-to-apples comparison between manufacturers, defines how rated CV and characteristic are measured, forms the technical basis of most modern valve data sheets. Design engineers who do not understand IEC 60534 often misinterpret vendor data and unknowingly act valves that cannot meet service conditions. ISA S75 sizing standards. ISA S75 standards parallel IEC methods and are widely used in North America and legacy specifications. Key focus areas: control valve sizing equations, expansion factor definitions, choked flow criteria, terminology alignment. Practical insight: ISA and IEC methods generally converge, but not always identically. Mixing equations or assumptions across standards leads to sizing errors. Specifications must clearly state which standard governs sizing and testing. Ambiguity here becomes dispute later, often during commissioning. Valve data sheets. The datasheet is the single most important control valve document. It is where design intent is either preserved or quietly lost. Mandatory versus optional data. Mandatory data, fluid properties at all operating points, design, normal, and minimum flow, inlet and outlet pressures, temperature range, required CV and valve characteristic, body, trim, and packing materials, end connections and rating class, fail action and actuator type. Optional, but often critical, data, noise limits, cavitation or flashing expectations, special trims, fugitive emission requirements, inspection and testing levels. Omitting optional data often forces vendors to make assumptions that rarely favor control quality. Common specification errors. Most datasheet failures are conceptual, not clerical. Frequent mistakes, single operating point instead of range, unrealistic pressure drops, ignoring minimum flow conditions, conflicting material requirements, overly tight shutoff with undersized actuators, copy-paste specifications from unrelated services. A datasheet filled perfectly with wrong assumptions produces a perfectly manufactured wrong valve. How datasheets influence final performance. Once released, the datasheet drives vendor sizing decisions, defines trim selection, fixes actuator margins, locks in performance limits. Every missing or ambiguous entry reduces the designer's control over the final product. By the time the valve reaches site, changing behavior becomes expensive or impossible. Inspection and testing. Image testing is where design assumptions are validated or exposed. Hydrostatic tests. Hydrostatic testing verifies pressure integrity, not control performance. Purpose: confirm body and bonnet strength, detect casting or fabrication defects, validate pressure rating compliance. Limitations: perform with water, does not represent actual service conditions, does not test dynamic behavior. Passing hydro does not mean the valve will control, it means it will not burst. Seat leakage classes. Seat leakage testing defines shutoff performance under controlled conditions. Leakage classes define allowable leakage rates, tested at specified pressures, highly dependent on seat material and finish. Engineering trade-off: tighter leakage, higher seat load, higher friction, degraded controllability. Leakage class must be selected based on process risk, not habit. Functional testing. Functional testing is the most valuable and most overlooked test stage. Includes stroke verification, positioner calibration, fail action confirmation, Response observation, travel smoothness checks. What it reveals: assembly issues, excessive friction, incorrect fail logic, poor dynamic behavior. A valve that passes functional testing cleanly is far more likely to perform well in the plant than one that only passes pressure and leakage tests. Standards, datasheets, and testing are the invisible control elements of every valve project. When treated casually, they allow risk to leak quietly into the system. When treated seriously, they lock in performance long before the valve ever sees process fluid. This is how design intent survives contact with reality. Installation, maintenance, and diagnostics. Designing for the entire life cycle. This final module closes the loop from design intent to long-term performance. Control valves do not fail suddenly, they drift. Most performance losses are seeded during installation, amplified by maintenance shortcuts, and only recognized when diagnostics are ignored. Engineers who design for the full life cycle, installation, operation, maintenance, diagnostics, build systems that stay controllable years after commissioning. Installation best practices. Image installation is the first real-world test of a valve design. Poor installation can negate the best sizing, materials, and actuation decisions. Orientation. Valve orientation affects gravity loads, drainage, and mechanical alignment. Key principles: actuator weight must not sideload the stem or shaft. Vertical stem-up orientation is preferred for globe valves. Rotary valves must account for shaft loading and bearing stress. Drainability matters in flashing, condensate, and corrosive services. Incorrect orientation accelerates packing wear, stem friction, seat misalignment. Orientation errors often show up months later as mysterious control degradation. Piping affects valves interact with piping more than most designs assume. Critical considerations: adequate straight runs upstream and downstream, avoidance of elbows immediately at valve inlet, uniform flow profile entering the valve, avoidance of piping-induced vibration. Consequences of poor piping geometry: distorted flow characteristics, increased noise and cavitation, erratic valve gain, reduced trim life. A valve cannot correct a distorted velocity profile, and accessibility. A valve that cannot be accessed will not be maintained. Design for access means clearance for actuator removal, space for packing adjustment or replacement, visibility of position indicators, access to air connections and positioners. Lifecycle reality: valves that are hard to access are maintained less. Valves that are maintained less degrade faster. Degraded valves destabilize loops. Accessibility is not a convenience, it is a reliability requirement. Maintenance considerations. Image maintenance strategy determines whether a valve ages gracefully or catastrophically. Wear components. Not all valve parts age equally. High wear components: trim, plug, seat, cage, packing, seals and bearings, positioner, pneumatic components. Design implications. Modular trim reduces downtime. Replaceable seats extend valve life. Standardized spares reduce outage duration. Ignoring wear paths during design guarantees higher life cycle cost. Predictive maintenance concepts. Modern plants are shifting from time-based to condition-based maintenance. Predictive indicators include increasing friction, slower response, rising air consumption, position deviation under steady signal. Advantages: maintenance performed when needed, not too early, not too late, reduced unplanned shutdowns, extended valve life. Predictive maintenance begins with designing valves that can be diagnosed. TASH diagnostics and performance monitoring. Image diagnostics turn control valves from passive hardware into measurable control assets. Signature analysis valve signature testing captures force or torque versus travel. What it reveals: packing friction levels, seat wear progression, stem misalignment, mechanical damage. Baseline signatures taken at commissioning become the reference for the valve's entire life. Without a baseline, diagnostics become guesswork. Friction trending. Friction does not jump, it creeps. Trending friction over time reveals packing degradation, corrosion buildup, seal hardening, early-stage mechanical failure. Control impact: increased deadband, slower disturbance response, limit cycling. Catching friction early prevents control loss before operators notice instability. Digital valve health metrics. Smart positioners enable continuous valve health monitoring. Key metrics: travel deviation, cycle count, air consumption, response asymmetry, time near seat or full open. These metrics answer critical questions. Is the valve still controlling or just moving? Is maintenance improving or degrading performance? Is the valve approaching functional failure? Digital diagnostics shift maintenance from reactive to evidence-based engineering. Installation, maintenance, and diagnostics define whether a control valve is a one-time purchase or a long-term control asset. Engineers who design for lifecycle behavior, not just initial performance, create plants where control quality improves with time instead of eroding quietly. This is where good valve engineering becomes great systems engineering.